Welcome. Today we are going to discuss the second module of 6th chapter. In this we shall discuss surface integrals. In the earlier module of this chapter, we introduced the notion of surfaces. In this module, we start with the notion of surface integral. Let T be a region in R2 and let sigma from T to R3 be a parametric surface. Also let S equal to sigma T. We further assume that the map sigma from T to S is bijective and continuously differentiable. Let f be a bounded scalar field defined on the set S. Then the surface integral of f over S is denoted by double integral f ds and is defined as follows. Surface integral of f over S is equal to double integral over T f sigma uv norm sigma u cross product sigma v du dv, provided the double integral under consideration exists. As f is a scalar field defined on S, f sigma uv is a real valued function of two variables u and v. The same is true for norm of sigma u cross sigma v. Hence, the above definition is well defined. Now, some observations. In the above definition, if we consider f to be the constant scalar field with value 1 at each point of the surface, then we have surface integral of f over S equals double integral over T f sigma uv norm of sigma u cross sigma v du dv, and it equals with double integral over T norm of sigma u cross sigma v du dv. And we know it is nothing but the area of the surface S. If we compare between the concepts of line integral and surface integral, we notice that for both the concepts we require a parametric representation for the domain of the scalar field or the vector field under consideration. However, the differences between these two concepts are the following. First, in case of a line integral, we integrate a smooth scalar field over a smooth curve. However, the notion can be extended to piecewise smooth curves. On the other hand, in case of a surface integral, we integrate a smooth scalar field or a smooth vector field over a smooth surface. However, the notion can be extended to smooth surfaces for whom the collection of all singular points is a set of content 0. Secondly, in case of line integral, the mathematical tool used is inner product and then Riemann integral. For surface integral, we require the notion of cross product of vectors in R3 and then double integral. And in case of vector field, inner product is also required. If the surface S is defined explicitly by an equation of the form z equal to fxy, then its parametric form is given by sigma uv equal to order triplet uv fuv for every uv in T. Thus, we find the cross product sigma u cross sigma v equals the order 3 tuple minus del f del u minus del f del v 1. And consequently, the surface area of S is given by area of S equals double integral over T non-negative square root of 1 plus del f del u square plus del f del v square du dv. If further f is a constant scalar field, say the value of f is c everywhere, then the surface is given by z equal to c. That is, it reduces to a part of a plane which is parallel to the xy plane lying above a height c above xy plane if c is positive and below a height c mod c if c is negative. Then del f del u and del f del v both are 0, and we find that area of S equals to double integral over T du dv. As both S and T have the same area, this agrees with our known formula for evaluating areas of bounded plane regions. One remark at this point: the surface integral of f over a surface S is sometimes called integral of f with respect to an elementary surface area ds extended over S. The symbol ds stands for elementary surface area. Now we are going to discuss the effect of surface integral under reparameterization. Let T be a region in R2 and let sigma from T to R3 be a surface. Also let S equal to sigma T. We further assume that the map sigma from T to S is bijective and continuously differentiable. We suppose that R is another region in R2 and there exists a bijective and continuously differentiable map mu from R to T. So, corresponding to every ordered pair UV in T, there exists unique ordered pair ST in R such that mu ST equal to UV. As composition of two continuous maps is also continuous, it follows that sigma compose mu from R to R3 define a surface. Let us denote lambda equal to sigma compose mu. We have shown this with the help of a diagram. Here R and T are two regions where T is equal to mu R and sigma from T to S is a surface and lambda is the composition of maps mu and then sigma. Then it follows that lambda S cross lambda T equals Jacobian del uv del st sigma u cross sigma v. Moreover, the maps sigma and lambda and their corresponding parameterizations are called smoothly equivalent. Clearly, as I said, the collection sigma uv where uv is from T and the collection of lambda st where st is from R are identical and both are equal with S. Now, double integral over R f st norm lambda s cross lambda t ds dt equals with integral of over R f of sigma uv norm Jacobian del uv del st sigma u cross sigma v ds dt. So, we take the modulus of the Jacobian outside and finally this integral equals with double integral over T f of sigma uv norm sigma u cross sigma v du dv. Hence, we have the following result: surface integrals remain invariant under smoothly equivalent reparameterizations. Now, we are going to discuss surface integral from another viewpoint. Let T be a region in R2 and let sigma from T to R3 denote a surface. Also, let S equal to sigma T. We further assume that the map sigma from T to S is bijective and continuously differentiable. In case S is a smooth surface, we have seen that both sigma u and sigma v are continuous and hence the collection sigma u sigma v forms a basis for the tangent plane to S at the concerned point. Hence, the vector field n on S defined by n equal to sigma u cross sigma v is perpendicular to each vector lying on the tangent plane. Hence, n is normal to the surface. The unit normal vector to the surface is given by small n. This is n by norm n. So, it is 1 upon norm sigma u cross sigma v times sigma u cross sigma v. Let F from S to R3 be a smooth vector field with components F1, F2, F3. Then for every UV in T, we find that inner product Fn applied on sigma UV equals inner product F sigma UV with N sigma UV. So, it equals with inner product of F sigma UV with norm of sigma U cross sigma V at UV N sigma UV, and this equals with norm of sigma U cross sigma V UV inner product F sigma UV N sigma UV, where norm of sigma U cross sigma V at UV equals with norm of sigma U UV cross sigma V UV. From the definition of surface integral, it follows that integral over S inner product Fn equals with double integral over T norm of sigma U cross sigma V inner product F sigma UV small n sigma UV du dV. Now, surface integral of inner product F and small n over S equals double integral over T norm of sigma U cross sigma V inner product F sigma UV small n sigma UV du dV. So, this equals with 1 upon norm sigma U cross sigma V double integral over T norm of F sigma UV capital N sigma UV du dV. We have already deduced that N UV equal to sigma U UV cross sigma V UV, and that equals with the triplet Jacobian del yz del UV UV, Jacobian del zx del UV at UV, Jacobian del xy del UV at UV. Hence, inner product of F and N at UV equals with inner product of the vectors, first one F1 sigma UV, F2 sigma UV, F3 sigma UV with Jacobian del yz del UV, Jacobian del zx del UV, Jacobian del xy del UV at UV. So, this equals with F1 sigma UV multiplied with Jacobian del yz del UV at UV, and this quantity added with two similar terms. From the above, it follows that surface integral of inner product F small n over S equals double integral over T F1 sigma UV Jacobian del yz del UV at UV du dV added with twice similar terms, where F1 is replaced by F2 and F3 and the Jacobians are also replaced. So, this equals with integral T F1 del yz del UV du dV plus two similar terms when we write in short. Now, for I equal to 1, 2, 3, let us denote Fi sigma UV equal to Fi x UV, y UV, z UV, that is Fi xyz. Also, we denote the Jacobian del yz del UV du dV as dy wedge dz and so on. We find dz wedge dy equal to Jacobian del zy del UV du dV, and this equals with the negative of Jacobian del yz del UV du dV, which is nothing but dy wedge dz. So, the wedge product is skew symmetric. We can find two similar results. Consequently, dx wedge dx equals with dy wedge dy equally dz wedge dz must be 0. Using the above notation, we can express surface integral of inner product f and ds over s equals with double integral over T f1 xyz dy wedge dz plus double integral over T f2 xyz dz wedge dx plus double integral over T f3 xyz dx wedge dy. The three integrals mentioned in the right hand side of the above equation are also considered as surface integrals. Now, since small n is a unit vector, its components are its direction cosines. Obviously, we are mentioning here the components along the coordinate axis. Hence, we can express n equal to cosine alpha 1, cosine alpha 2, cosine alpha 3, where alpha 1, alpha 2, alpha 3 are the angles n make with the positive directions of xyz axis. This enables us to write inner product Fn equal to inner product of f1, f2, f3 with cos alpha 1, cos alpha 2, cos alpha 3, and that equals f1 cos alpha 1 plus f2 cos alpha 2 plus f3 cos alpha 3. Hence, surface integral of inner product Fn over the surface S equals with integral over S f1 cos alpha 1 plus f2 cos alpha 2 plus f3 cos alpha 3 ds. This equals with double integral over S f1 xyz dy wedge dz plus f2 xyz dz wedge dx plus f3 xyz dx wedge dy. Next, we consider a surface described by an explicit formula z equal to fxy. In parametric form, it is expressed as sigma from T to R3, where sigma uv equal to uv fuv for every uv from domain of F. Let small n denote the unit normal to the surface S equal to sigma t, which has non-negative z component. Also, let F equal to f1, f2, f3 be a differentiable vector field defined on S. We have already seen sigma u cross sigma v equal to minus del f del u minus del f del v 1. Now, surface integral over S inner product Fn ds equals to double integral over T inner product of f sigma uv n sigma uv du dv. This equals with double integral over T minus f1 del f del u minus f2 del f del v plus f3 du dv, where f1, f2, f3 are evaluated at sigma uv, that is uv fuv, and del f del u del f del v are evaluated at uv. Next, let phi be any scalar field defined on S. Then the surface integral of phi over S equals with double integral over T phi xyz norm sigma u cross sigma v du dv. This equals double integral over T phi uv fuv norm of minus del f del u minus del f del v 1 du dv. So, this equals double integral over T phi of uv fuv non-negative square root of del f del u square plus del f del v square plus 1 du dv. Moreover, surface integral of phi xyz dy wedge dz over S equals double integral over T phi uv fuv Jacobian del yz del uv du dv. This equals with double integral over T phi uv fuv. Now, we expand the Jacobian determinant, so it becomes del y del u del z del v minus del y del v del z del u du dv. Putting the values, we find this equals with double integral over T phi uv fuv multiplied by minus del f del u uv du dv. Since x equal to u, y equal to v and z equal to fuv on the surfaces. So, this equals with the negative of double integral over T phi uv fuv del f del u uv du dv. In a similar fashion, we can show that surface integral over S phi xyz dz wedge dx equals with negative of double integral over T phi uv fuv del f del v at uv du dv and double surface integral over S phi xyz dx wedge dy equals with double integral over T phi uv fuv du dv. Now, we are going to introduce some differential operators on R3. In the remaining part of this module, we shall consider a rectangular Cartesian coordinate system xyz on R3. Let A be an open subset in R3 and f from A to R be a smooth scalar field. Then the gradient of f is denoted by grad f or nabla f and is defined as nabla f xyz equal to del f del x del f del y del f del z evaluated at the point xyz. So, from this we can consider nabla f as an operator which is del f del x del f del y del f del z, that is we can consider this as del del x del del y del del z operating on f. Being motivated from this, let us introduce a differential operator nabla by nabla equal to order triplet del del x del del y del del z. Now, we see whether the operator nabla can be combined with some smooth vector fields. Let A be an open set in R3 and f from A to R3 be a smooth vector field. Let f equal to f1, f2, f3. The divergence of f is defined as a scalar field on A denoted by div f or nabla dot f, that is inner product of nabla and f, and defined as follows. Divergence f equal to as inner product del del x del del y del del z and f1 f2 f3, which is del f1 del x plus del f2 del y plus del f3 del z. This means at any point xyz in A, divergence f at xyz equals del f1 del x xyz plus del f2 del y xyz plus del f3 del z xyz. Since the vector field f is smooth, the scalar fields f1, f2, f3 are also so. Hence, the above quantity is well defined. Now, if small f is a continuously differentiable scalar field, then nabla f is a vector field. Consequently, if the partial derivatives of small f are also continuously differentiable, we have divergence of grad f equal to nabla dot nabla f that looks like inner product of del del x del del y del del z with del f del x del f del y del f del z. So, this equals del 2f del x2 plus del 2f del y2 plus del 2f del z2. We denote this nabla square f. We call this the Laplacian of f. It is trivial that here by the symbol nabla dot f or inner product nabla f is not actually the inner product, only use the notation as the operation looks similar. Next, let capital F be a smooth vector field as mentioned above. Then the curl of capital F is a vector field defined on the set A. It is denoted by curl F or nabla cross F and is defined as follows. Curl F, that is nabla cross F. We write this using a notation looking like determinant. In the first row ijk, second row del del x del del y del del z, and third row f1 f2 f3. So, it equals with the order triplet del f3 del y minus del f2 del z, del f1 del z minus del f3 del x, del f2 del x minus del f1 del y. This implies for all xyz in A, curl f xyz equals del f3 del y xyz minus del f2 del z xyz and to similar components. Result. Let A be an open set in R3. F and G be two vector fields whose components are f1, f2, f3, g1, g2, g3 respectively. We assume that these components are continuously differentiable at least twice over the set A. We further assume that phi is a smooth scalar field having second order continuous partial derivatives on the set A. Then f plus g phi f, f cross g and nabla cross f are smooth vector fields whose components are continuously differentiable at least twice. The case is same for the scalar fields f dot g, nabla dot f, etc. Hence, we have the following result. The first result we have shown in the calculations. Divergence of f plus g equals with divergence f plus divergence g. That is, divergence is additive. Second result, we have shown here the calculations. Curl of f plus g equals with curl f plus curl g. Third result, divergence of phi f equals with grad phi dot product with f plus phi divergence f. Fourth, curl of phi f equals with grad phi cross f plus phi times curl f. Fifth, divergence of f cross g equals with curl f dot g minus f dot curl g. Sixth, curl of f cross g equals with g dot nabla f minus g nabla dot f minus f dot nabla g plus f nabla dot g. Also, we have shown that for any smooth scalar field phi, curl of grad phi equals to theta. That is the zero vector in R3. Now, del dot nabla cross f equals 0, that is divergence of curl f should be 0. Now, nabla cross f equals with nabla dot f minus nabla square f, that is curl of curl f equals grad of divergence f minus Laplacian f. So, in this module, we discussed the notion of surface integrals, and after that we studied some differential operators and their properties. We conclude here.